Hey, college algebra. It is Mr. McCune here. I'm at home. I'm with my baby. It's been good, and I wanted to go over this with us because we didn't have that much time to get over it and want to make sure you had some explanations before heading into the test on Thursday. You guys have been great this year. It's been so fun to spend this semester with you, and we're closing out in just a couple of days. So let's finish well and start with this test. So this is the homework quiz key. If you would pull out your homework quiz, this would be a good chance to go over some of these questions and take a look at a glimpse of some of the questions that you may see on the test. We'll also take a look at the problem set that you had on Monday and look at some of those as well. And if you have any other questions, please just shoot me an email and try to get those answered for you and set you up for Thursday. All right, so some vocab to be aware of. Let's see. Instead of all possible outcomes in an experiment, we need to know that this is called the sample space. And one of the most important things you're going to need to be able to do on the test is define the sample space. And we'll look at that in some of the examples down here. So right along with sample space, make sure you understand the event as well, that an event happens within a sample space. And that's how we determine the probability. All right, now when we want to find the number of ways of picking R objects from N objects in order does not matter, we use combinations, and you all knew this. This is something that you guys have been great on, and if order does matter, we have permutations, and a special type of permutation, of course, is if there are, within that set of those objects, if there are some repeats, then we may have a distinguishable permutation situation. And if we're just counting distinct events, like date night, that kind of thing that we talked about, or a menu, um, that would be the fundamental counting principle. We'll look at some of those too. All right, so the first question on the quiz was, I think the question was, what is the probability of being dealt 5 face cards? And the best way to start one of these questions is to think, what is the sample space? And then what are the events? So find n of s and find n of e. So the number of the sample space of objects in the sample space, number of objects in the event that we want to see happen. So the probability of being dealt 5 face cards. Well, first we need to know how many face cards are there in a deck. Well, there are 12, so we'll visit that down here. Jack, Queen, King, so 3, and there's 4 suits, so 3 times 4 is 12. So don't worry if you didn't know that. That information should be provided for you, so don't think you need to know cards inside and out. But there will be 12 face cards. That'll be important. So let's start with the sample space. Let's start big. The sample space would be, well, we are choosing 5 cards, right? We're being dealt 5 cards, and there are 52 total. So it's 52 combination 5, and it's that way because order doesn't matter. We don't care what our hand looks like. We care what it looks like, but we don't care what order we get the cards in. It doesn't matter if it's if we get, the jack first and then the king and queen. Just so long as we get 5 face cards, that's all we want. So 52, choose 5, or 52 combination 5. That is the sample space. That is all the possible outcomes. And then the event that we're looking for is being dealt 5 face cards. Well, what's the probability of that? How many ways can that happen? Well, there are 12 face cards, but we are just choosing 5 of them. So it is 12 combination 5, and the order doesn't matter. Again, we don't care the order we get those 5. So if that's our event and that's our sample space, then the probability of that event happening is the number of ways that event can occur divided by the number of total possible outcomes. So 12 combination 5 divided by 52 combination 5, and that would give us this long decimal, or if I converted it to a kind of an odds of 1 out of, it would be about this right here. So that is that one. That is a great one. Defining the sample space, defining the event space. Make sure you're comfortable doing that. Similar thing happens in question number 4. So this is the one where you have 8 balls that you're choosing out of a jar, and there's 5 white ones and there's 3 red ones. So 8 total balls, and part A is, what's the probability of choosing 2 red ones? So first, our sample space. There are 8 total, right? 8 total in the jar, and we're just going to choose 2 of them. So it's 8 combination 2. 8 combination 2. We don't care about the order. We're just going to choose 2. And we want to know about choosing red. Well, how many red are there? There are 3 red, and we want 2 of them. So it would be 3 combination 2. So once again, if the probability of the event happening is the event number of events that we want, favorable outcomes over number of total possible outcomes, then it is 3 combination 2 divided by 8 combination 2. And when you work that through your calculator, you will come up with a response like this. And then part B says, well, what about white balls? Well, it would be just almost the inverse of that, right? So if for the red ones it was 3 choose 2, for the white ones, since there are 5 white balls, 5 choose 2. And what about the sample space? Well, there's still 8 of them and we're still choosing 2, so it's the same sample space. And so we would expect that we would have a higher probability if there are more white balls, and we do. 1/3 is higher than 1/9. So make sure you can follow that right there. Again, we define the sample space, we define the number of favorable events that we wanted to see happen, and we plug that into our formula for finding probability. All right, number 33. This one was interesting in that it used fundamental counting principle and not just combinations as we had seen in the previous two. So this was a true-false test, given a true-false test, and what is the probability of, if there are 10 questions, getting all of them correct the first time? That was part A, and then part B was, what about just getting 7 correct? So 10 true-false questions. So you have to ask yourself, there's 10 questions. So again, use your intuition, think about spaces. There are 10 spaces, right? 1, 2, 3, up to 10. Those represent the different questions, right? Each 10 question. How many outcomes for each question? Again, think about an outfit you're putting on. Remember, you could have shoes, pants, shirt. And how many shirts do you have? How many pants? How many shoes or shirts? I forget which one I said first. And you're filling those spaces with the total possibilities. So in space 1, there are 2 possible outcomes, right? True or false. And question 2, true or false, and so on. And so if there's 10 questions and 2 possibilities for each one, then our sample space, the number of total possible outcomes, is 10, or 2 to the 10th. 2 to the 10th. Now the number of events we're looking for is we want to get 10 right out of 10 questions. So there's 10 questions and there are 10 favorable outcomes we're looking for. Well, that's 10 combination 10, and that is just 1. And if you think about it, there's only one way to get the test right? There's only one way to get everyone right. So you can use your intuition there. So the probability of the event happening is 1 possible outcome, or 1 favorable possible outcome, over 2 to the 10th possible, total possible outcomes, which is a big number. So 1 over 124. So it's about 1 in 1,000, or about 1,000th when you work that out. Now we should expect our probability to go up in part B, where there are 7 possible, or we just want 7 correct. 7 correct in a true-false test, walking in knowing nothing. How many of you ever done that? Walked into a test and know nothing? How many of you done that in a college algebra test? All right, don't raise your hands too fast. We're going to finish this year well, right? So the sample space is still the same. Still the same. Just a minute, and I'll be right up. That's my daughter, guys. We're going to do an Easter egg hunt. So the sample space is the same. It is 2 to the 10th. 2 to the 10th is the sample space. And the event that we are looking for, well, we want to get 7 right. And think about it. Does order matter? Does it matter if we get the first 7 right or the last 7 right, or 2 right and we get 1 wrong and 1 right and then 1 wrong? And however, you could think of lots of different ways, but we don't care about the order of this happening. That would be a permutation if we did. We just want to get 7 right somehow, and we want to get exactly 7. So that would be, if there are 10 questions, we want to choose 7 of them correctly. So it would be 10 combination 7. So that is our event space. So again, our probability is the probability of getting that event happening. So 10 combination 7 over the total possible outcomes, which is 2 to the 10th. And indeed, our outcomes are a little higher. And look, that's a little more than 1/10. So 1 out of 8 times, if you walk in, you could get a 70. Who knows? So think about that. Will you take those odds? All right, so that one used permutations. All right, the backside. You guys did a great job writing some questions here. I love reading your responses. That's one of the most fun parts about what I do, getting to see you engage when you write it and you see, hey, it's actually kind of challenging to do these sometimes. All right, so let's run through some examples of what you might see. Fundamental counting principle. Okay, some examples, and we've gone through this before, but just so you're familiar, here's some written out. Read through these. Make sure you're familiar of when to use fundamental counting principle, when to use permutation, combination, and so on. One thing to recognize is some things that that are pretty close here. For example, choosing a string of numbers or letters. So that's, you might be given your name. You might be given the name Dave and said, how many ways can you rearrange Dave? And that would just be a permutation if it was just that. But if it said, hey, there's repetition, you can choose a D and then choose a D again or something. You put them in the bag, you pull them back out. Well, in that case, it's not a permutation because there's 4 choices every time. So watch for the repetition or not. And then also look for something like this. Think about the letters like, well, the first letter can't be a vowel, so it has to be a consonant. So if you restricted that first space, that's kind of like, the when we were electing a student body government and we say, oh, the president has to be a senior or something like that, or the committee chair has to be a Democrat or Republican or whatever it is, and we restrict it to a smaller set for that first one, and then from then on it looks like a permutation. That ends up being fundamental accounting principle, depending on how you look at it, because you have to restrict that first space. So look at some of those examples. Permutation, we're great with those. You seem to really understand. Make sure you're familiar with this formula right here, the NPR formula, and how it differs from the NCR formula by this R factorial right here. And remember, you can often use permutation. You can use your intuition with permutation. So if there's race finishers, if there's 30 people in a race and there's 3 finishers, well, how many possible ways could they finish? Well, if there's 3 finishers, then 30 for the first place, then 29 for second place, and 28 for third place. So 30 times 29 times 28. Use your intuition, but also know how that fits into this formula here. It would be 30 factorial over 30 minus 20, or 30 minus 3 factorial, which would be over 27, which would leave you with 30 times 29 times 28. So I know that's a lot. I'm jamming this in, and you're not seeing it written out, but you guys get that. I messed up here. I started writing the definitions for combinations instead of distinguishable permutations, but important things to know again, remember, use this formula with the R factorial out front. So again, permutation order does matter, combinations order doesn't matter. With combinations, that will show up a lot in our probability questions when defining the event space and when defining the sample space. So make sure you're very comfortable using that. Distinguishable permutations, again, rearranging the letters in a word. We say Mississippi, how many different ways can you rearrange that? Or Atlanta, or your name, or whatever it is. Those you seem to be great with as well, and those will also pop up in a probability question here and there when you're defining the event space or maybe even the sample space. So be aware that you could use any of these methods of counting to define the event or the sample space. All right, last question to go out on, and we'll end this video because it's kind of running over a little bit. Hopefully it's helpful to you guys. The last question that we put as the bonus is was this. It said a boss says, hey, 6 employees are going to be chosen from 30. So I'm going to choose 6 to give a bonus to. And they're all going to get the same bonus. So order doesn't matter. So right away we know we're going to use a combination somewhere. And then the question says, what is the probability that that no woman is chosen? No woman is chosen. So that's the question. You can go back and look at it. We'll get to that second part in a second, but let's just look at the sample space first. Again, anytime it's a probability question, let's look at the event space and the sample space. So let's look at what are the favorable events that we want to see happen? What are the total possible outcomes that we could have? So for 6 employees chosen from 30, we're just going to choose 6 from 30. If it was just that, if that was just the question, how many different ways can 6 employees be chosen from 30 to get the same prize? It would be a combination because order doesn't matter. It's all the same prize. So our sample space, total possible outcomes, is 30 combination 6. So we got that out of the way. We're able to define that right away. Then the trickier part, what is the probability of not choosing a woman? What is the probability of not choosing the woman? Well, we have to realize not choosing a woman, that'd be the same as choosing a man every time for all 6 spaces. Well, if there's 11 men, and I think there were 19 women, 11 men in this question, so if there's 11 men, then the probability or the number of ways we could choose 11 men, or choose 6 men, right? We're choosing 6. If there are 11 of them, it would be, and this is our event space, 11 combination 6. All right, so make sure you get that. That would be the ways that we could not choose a woman, is choose all men. And they've used these kind of things in court cases to say, hey, there was sexism going on here. And mathematicians, it actually turns out very fascinating. Mathematician is currently rated as the #1 best job to have in America right now. So something interesting for you to think about when you're like, why would I ever use this? Statistician is number 3, but the cushiest jobs get about $100,000 a year and a great lifestyle. So interesting. Maybe you want to hang in there. So, probability of this event happening if our event space, our favorable outcomes are 11 combination 6. And I guess this is unfavorable in this case, it's just what we're looking for. And the sample space is 30 combination 6. We run that through our calculators and we get this long decimal right here, which turns out to be 1 in every 1200 times. So not very likely to happen. All right, guys, hopefully that helped you out a little bit. I'll try to check back in later and get you a short run through of the problem set number 3 as well. But hopefully this is helpful. Again, be familiar with all the different methods of counting. Be very familiar with finding probability, defining the sample space, and defining the event space. Very important. You guys will do very well. And I'm proud of you guys, and we'll see you soon.